In this video, we're going to look at how we can find the identity element and the inverse algebraically. Now, this is perhaps straying into year 2 content, but given that we looked at associativity and commutativity and closure, algebraically, it sort of makes sense to practice it with identities and inverses. So let's start with identities. So we've got a binary operation on the set of real numbers. Our binary operation is written out algebraically, which is why we're probably going to have to do this process. It's an infinite infinite set of a group of real numbers, so we can't draw out a Cayley table, so we're going to have to do it algebraically. Now, just a reminder of our definition of our identity element. It is A combined with our identity E should be equal to A. The identity should not change the element A. So we're going to substitute directly into this equation in order to figure out what E is going to be. Okay, so what I'm going to do is I'm going to write A. So what I'm going to do is now substitute A in for A in my binary operation. So this here. And I'm going to substitute the E in for B in my binary operation because it's my right element. So what I'm going to get is, if I substitute for this A first, I'm going to get A. And then we're going to replace the B with an E, so plus E. And then we got our subtract 5. So subtract 5 is equal to A. Now I have an equation which I can solve for E. So I'm going to start by subtracting A from both sides to get E subtract 5 is equal to 0. And then rearrange to get E is equal to 5. Now 5 is a real number. Okay, so that sort of makes sense. This is a possible identity element. Now I say possible because in my definition of my identity, I wrote that A combined with E is equal to A. But also, if I swap the A and the E around, that statement should still be true. Okay, we should get E combined with A is also equal to A. So we do just need to check that. Okay, because right now we've only established it would work as 5 if it's on the right, but we do need to check if it works if it's on the left to ensure we have a proper identity element. So what I'd be doing is I would be doing 5, our identity on the left, combined with A. So I'm going to substitute into our binary operation, and 5 would be my A, whereas A would be my B because it's on the right. So I would replace this A with a 5. I'd replace this B here with an A, so plus A, and then I'd write subtract 5, like that. Now, if we simplify, we end up with A, which is what we're expecting, okay? Because when we took our possible identity and combined it with A, we ended up with A. So therefore, we can establish that 5 is the unique identity inverse set. Now that's identity done. Let's move on to inverse elements, which I'm going to do on the right. So just a reminder of our definition of our inverse. Any element A combined with its inverse should be equal to our identity. So in order to establish our inverse, we need to know our identity first, which we've established as 5. So I can go to this statement here, and I'm going to substitute in 5 for E, like that. Now I'm going to use my binary operation, okay, and I'm going to substitute in the A and the inverse of A. So A is my left element here, so I would replace the A with it, whereas my right element up here is called B, so I'm going to replace that with the A to the minus 1. So let's go through. So this A stays the same. Then the B gets replaced with the inverse of A, so plus the inverse of A, and then we got to subtract 5. And that is equal to 5. Now we're going to rearrange to find the inverse. That's the idea here. So we're going to add 5 to both sides to get A plus its inverse is equal to 10. And then I'm going to subtract A to get that the inverse is equal to 10 subtract A. Now the answer has come out in terms of A, but that is fine because every element A will have its own unique inverse. So it makes sense that we need to substitute a value in A, and then we're going to get the specialized inverse for that value. This was different to the identity, where the identity had to come out as one specific unique value in order for it to be an identity. If this here had come out as 5 subtract A, then we could establish there is no unique identity, because that would imply that the identity depends on A, and therefore would get a different identity for every single element, which doesn't make sense. Okay, so it makes sense that it's come out as 10 subtract A. The only thing we just need to clarify is 10 subtract A a real number? Because our inverse must also be a real number, because that is the set we're working on. Okay, and 10 subtract A is indeed a real number, given that A is a real number. So what we also need to do next, just like we did with the identity, is we've shown this inverse comes from doing A combined with the inverse is equal to 5. But we do need to just also verify that the inverse A on the left combined with A does indeed come out as our identity, which is 5. So we need to verify this statement. So essentially the combination I need to do is our inverse A, which was the 10 subtract A, combined with A. And I just need to check that this simplifies down to 5. So our left element is 10 subtract A, so that would be our A in our binary operation, whereas our right element is A, so that would be our B. Okay, so let's go through our binary operation. So I'm going to replace this A here with 10 subtract A. And then we're going to replace this B here with an A, so plus A. And then we got subtract 5 like that. Then let's just see how it simplifies. Well, negative A plus A is 0A. 10 subtract 5 is 5. Okay, so what we've got is what we'd expect. So therefore, we can conclude that each element in the set has a unique inverse 10 subtract A in the set.